Hello, welcome to the new class. And today we are going to delve deeper into Sommerfeld models. And um, so, just to recap, what we discussed last class was how Sommerfeld model is fundamentally different from Drude model, and how it depicts a different probability distribution function for the electrons, and how that completely changes the system properties. So we also discussed some physically intuitive differences between Drude's model and Sommerfeld model, like Drude's model says that every electron can participate in electrical or thermal uh, phenomena happening in the material. But for example, the Sommerfeld model says that only the electron which are on the top of the energy level of the filled energy bands will be able to participate in electrical or thermal phenomena that are happening inside the material. So there is a fundamental difference, and Sommerfeld model was actually very successful in predicting some of the electrical or thermal properties of the material. So, so what we now want to do is basically see that how Sommerfeld model works. But Sommerfeld model is far more complicated than Drude's model, and to understand Sommerfeld's model in the full clarity, what we need is a basic of quantum mechanics. So what I will start with is quantum mechanics and how we are going to classify and put electrons into the energy levels, how the energy levels are defined, and all those things. So that is what we are going to discuss today. So we are not going to discuss the Sommerfeld model in its entirety, but we are going to build up Sommerfeld model. So let us start with Sommerfeld model. So what we will cover here is the only the basics. How to set up a quantum mechanical system. Because now we are moving to quantum mechanics, we are moving to Sommerfeld model. What we want to discuss, what we want to learn more is the quantum mechanics behind the system. So how to set up a quantum mechanical system, and how to place electrons in it. So how does quantum mechanical systems work? That is what we are going to learn. How to place electrons in it. So that is what we are going to learn more or less in this class. So what I'm going to consider is the Schrodinger equation. Okay, this is the Schrodinger equation for, let's say this is a function of r, psi of r, v of r equals to e of r. So this is a Schrodinger equation for a single particle. Okay, this is a Schrodinger equation for a single particle. But now, what if we have a lot of particles? What happens then? Let's say we have a lot of particles. So what we generally do is we define a wave function which depends on every position of every particle. So it's called a many body wave function. This is called a many body wave function. So as you can see that this is intense, like this has a lot of variables. This is a multi-valued multi-variable function, and it has the coordinate values of, let's say, n particles. Here there are, let's say, n particles or n electrons, for example. But what happens is sometimes when there are um, no interactions between them, then we can simplify this many body wave function into simpler forms. So we are going to see how we can do that. So how will the Schrodinger equation look like for this n particles? The kinetic energy term here. So I am assuming that you know Schrodinger equation very well, and you can generalize it for more than one electrons. So let's say this is the kinetic energy term which calculates the kinetic energy of individual electrons. And what is the potential energy term? The potential energy term will see that how the potential energy, or yeah, how the potential energy between two electrons will be uh, interacting with the or will be affecting the trajectory of the electron. So that is what we are going to do. And now this is the modified Schrodinger equation. This is the operator, this is the whole operator, this is V operator, this is grad operator, and psi r1 r2 Rn equals to E psi r1 Rn. So this is the Schrodinger equation of the combined system. But now the problem is that this is a very huge problem. Like this is, mathematically speaking, this is an absolute nightmare, because it has like arbitrary number of coordinates. The psi depends on arbitrary number of r, and we don't have any idea about how to handle this, because it's a two body function, r1 r1 r2 r2 r3 r1 r3. So it has a lot of combinations, so we don't really know what to do. So what we do here in Sommerfeld model is, we, instead of a classical ideal gas, we model the electrons as a quantum, the quantum we discussed earlier, ideal gas. So there is a difference, but it's still ideal. But and what is ideal gas? Ideal gas means that two electrons, they don't talk to each other, they don't interact. So we can forget about this term. So we can completely forget about this term, and we are left with this. So that is very fascinating, because it can significantly simplify the math. That's what, because we are assuming it to be an ideal gas, what it will do is it will significantly improve the math, and we will not have to deal with all these nasty this is like bad. This is mathematically, it's a bad, and it makes the computation a lot more, or most of the times impossible. It makes the computation or calculation impossible. But now we have this, what we can say is, from a basic intuition of quantum mechanics, we can actually, because the electrons are not talking to each other, so we can think that this picture, what if we can solve for the wave function of each individual electrons, because they are not talking to each other, they are just like identical particles which have exactly one operator, which is the kinetic energy operator. So it can be a function of the individual electronic wave function, psi 1 r1, psi 2 r2, psi and rn. So the size, the phi, this is called phi, sorry. So this is called phi, and this phi's I am defining, these are the individual electrons wave function, and I am trying to construct the whole electrons wave function from these phi's. But if I consider these phi's, then what does, and from now on, what we will do is we will deal with phi's, not psi's. We will see later how we can construct psi from phi. But because the rationale is the electrons are not interacting, we can see individual electrons and forget about everything else. So the only interaction they will do is the Pauli's exclusion principle. Pauli's exclusion principle, where two electrons cannot occupy the same quantum, occupy the same state. Okay. Okay, so now we come back to the phase, this single electron picture. So let us now focus on the single electron picture. Okay, so what we have is a very simple picture, and that is minus. Now we have come back to the single electron equation. This is the equation. And this is the equation for a free electron, obviously, because there is no potential term. There is no interaction between two electrons. There is no external potential also. So the electron is completely free to move. And what is the solution of this kind of equations? The solutions are generally of the form e to the power I k dot r. Yeah, so that is pretty much the solution um, of this kind of equation. So it's called a plane wave. It's called a plane wave solution because it's like a wave which is moving and which is completely delocalized. So there is no one place where you can find the electron because it is intuitively um, very clear because the electron is free. So electron is like basically electron is equally probable to be everywhere. But when we sometimes when we confine it to a volume, then there can be a normalization factor which can come into the picture. So that is a plane wave picture where the electron is completely free. But in real molecules, the electron is not free. So electron can be confined within a region, but within that region, the electron is free. So it can be thought of as that. So let's say we confine the electron within a box, within a rectangular box. Okay. And the dimension of the box is Lx, Ly, and Lz. So it's a cuboid. It's a parallel piped cuboid kind of box where we are um, just holding back the electrons. So the electrons are free to move wherever they want inside this box, but they can't leave this box. So this can be modeled as zero potential inside and infinite potential outside. So what it means that the wave function needs to drop to zero at the boundaries because there should not be any wave function at the outside the box, and because the wave function is a continuous quantity, so the wave function has to be zero also at the boundaries. So in all the boundaries the wave function has to become zero, and if we impose that after some math, what we can see is the psi of x, y, and z can be thought of as some normalization factor into sine n pi x by lx, nx pi x by lx, sine n y pi y by n ly, sine nz pi z by lz. So this is the wave function that we can see. Okay, so what we can think of this about this wave function, and what will be the energy? The energy is often given as nx square by l square lx square plus ny square by ly square plus nz square plus nz square by lz square. So this is what the energy will be. So this is often, so this can be a little bit of math, as in sometimes basically what happens is it's free, but it also has some boundary conditions where we are making the psi to be zero, and this sine function is the appropriate function, and the energy will also have a term which is this. So this can come if we just put this equation into the Schrodinger equation. Then we will get that the energy is given as this. Okay, so what happens now is very simple, that how does the energy surface look like? So these are now the nx, ny, and nz. Nx, ny, nz are called the quantum numbers. Now we can arrange the electrons, we can label the electrons as in some quantum numbers. For example, electron 1 is in quantum number nx1, ny1, nz1. The electron 2 is nx2, ny2, nz2, and so on. We can label the electrons like that. But if we want to visualize it more properly, what we can do is we can make an axis where we can label this as nx, this as ny, this as nz. Now instead of continuous variables we have discrete grids. So ny, nz and nx, ny and nz, they can only be integral values. So we have a grid, we have like a grid. So here also there is like grid points. It's basically grid point where the things can only take integral values. So what we want to see is how much of this, how much of these grids are filled and how much of these grids are empty. So now let's say ny and nx, for example, the epsilon is given. The epsilon is given. So the for example, the in the x-axis we can see if we want to get a more mathematically accurate argument, we might say that okay, nx, ny, and z, they are very small numbers. They are, maybe there are a lot of electrons, so they are really small. So they are like situated very in very dense manner. So we can assume that they are continuous for now, but we will later drop that assumption obviously. So epsilon is h square pi square by 2me into nx square by lx square plus ny square by ly square plus nz square by lz square. So if nx and ny are 0, for example, I want to see how far nz can be. If nx and ny are 0, then what it becomes, epsilon equals to h square pi square by 2me nz square by lz square. So nz becomes what, lz into 2me epsilon by h square pi square. So that it what it becomes, the nz becomes this. Similarly, nx becomes lx by h pi root, ny becomes ly by h bar pi, and nz becomes lz by h pi to epsilon me. And we can see that this is an equation of an ellipsoid. This is an equation of an ellipsoid. Ellipsoid is an ellipse but 3D. It's like a balloon. So it's like this. It's an ellipse in every plane, but it also has a, it's a sphere but elongated, elongated in some sides. So it's a ellipsoid where the semi-major axes are this A, B, and C. So yeah, so that is pretty much the semi-major axes are these. So it's an ellipsoid where A equals to Lx by B equals to Ly by h bar pi to epsilon me, C equals to Lz by h pi to epsilon me. So it's an ellipsoid. What is the volume of this ellipsoid? So what we want to do here, we want to correlate the energy of the electron and the number of the electron, the maximum energy that can be there to the number of the electron that is there. So it is 4 by 3 pi ABC, that is 4 pi by 3 Lx Ly Lz h cube pi cube 2 pi 2 epsilon me all to the power 3 by 2. Correct? So that what it says to us is that this is the volume, or this is the number of, this is more or less like a number of points what we have here. Right. So what now happens is that um, there are these many numbers of, let's say, the points. These many number of points are there. So what can be done is, but there is another catch here. The V effective is not V, because this V can also take negative numbers. So nx cannot be -1, ny cannot be -1. So all of them start from 0. So actually the effective V is 1/8 of V, which is just pi Lx Ly Lz by 6. I think there is yeah. So we can take the h bar and pi inside, and we will, after manipulating a little bit, what we will have is this. So this is the number of quantum states that are available for the electrons to take. So how many is the total number of electrons then? This. So let's say we can call this V of the box because it's a cuboid. So, and there are, per each quantum number there can be 2 electrons, because the electron can have plus spin and minus spin. So there is a spin quantum number also. So V by 3 pi square to 2 epsilon me by h square by 3 by 2. So that is Ne. So that's how what we did is, given the electron density, we could actually predict that how much is the highest energy that the electrons will occupy. So after we have got this equation, what we can say is that, let's say this is a coordinate system, and these are the ellipse, this is the ellipse, and on the surface of this ellipse, so in the center of the ellipse, the energy is less. But as we go out from the origin, the energy of these quantum states become more and more, because the energy, as we saw, is it goes like nx by lx whole square plus ny by ly whole square plus nz by lz whole square. Okay. So what is the maximum energy that the electrons can have? That is given as this. So the basic takeaway is this. So it has some dependence on E like that, and also the E depends on Ne to the power 2 by 3. So the maximum energy, or E max, increases as a 2/3 power of the total number of electron, or we can also say the electron density, because if we divide Ne by V, we get rho E, or the electron density, which is given as 1 by 3 pi square 2 epsilon me by h square to the power 3 by 2. So the electron density also, not only the number, but also the density can be related to the maximum energy like that. So that can give us a very good window into seeing that how can the maximum energy, why we care about the maximum energy at the first place, because we have discussed in the last class, the electrons at the maximum energy are the electrons which will be participating into electric and thermal phenomena. So we need to have a very good understanding of those electrons. How many electrons are they? Are they a very significant chunk of the total number of electrons? Are they not? How are their behavior? What is their energy? Can they jump to the empty states? Can they do something else? So all of this we need to know. And the first result we got in this line of thought is that the maximum energy for a free electron gas is dependent on the number density of electron to the power 2 by 3. So in the next class we will see that uh, how can we have some more information about these kind of systems, how can we extract more and more information, and how can we say that how we can use this information into electric and thermal conductivities, or electric or thermal phenomena happening in the material, and how can we match that with the experiment. So till then, see you and best of luck.